we left off talking about two different types of organometallics. We left off talking about granular reagents, which are made with magnesium as the metal, and Gilman reagents, which are made with copper as the metal. So we talked about how to make them. We talked about the optimal subtypes of reagents. So you can make these with, as we talked about here, like with the Gilman, it can be vinyl, it can be alkyl, or aerial. You can make either type. Right. It's the same thing with the granular. You can make alkyl granules, vinyl granules, or aerial granules. And then we left off talking about what you use these organometallics for. And one of the main uses is to make carbon-carbon single bonds. All right. So we talked about with the granular and the Gilman, how this works. We didn't go through the mechanism necessarily, and we won't do that, but we just talked about the outcome. So today we're going to look at these coupling reactions and kind of go through them and talk about what the expected outcomes are when you have a coupling reaction. Right. So one of the ways I like to talk about this is to simplify it down to the components. Right. So for a reaction like this, if you watch the organometallics video, then this is not new to you. I like to call CM is my organometallic. And then plus RX, where this is my coupling partner. Right. I normally X is a halogen, but it can be other leaving groups as well. It can be a triflate, like an OTF. It can be a tosylate. Right, there are other groups that X can be. So I don't just want to call it an alpha halide. It's a coupling partner. So the goal is to connect C and R. That's where my new carbon-carbon bond is going to come from. So when I run this reaction, this is the desired outcome where C and R are together. And then M and X. But normally this is just waste. All right, so when we're working through these examples, the way we work through them is to first identify C and M, and then identify R and X, and then put C and R together. So it's that simple. So in this first example, which one of those is the organometallic?
Magnesium oxide.
Yes, I agree. What type of organometallic is that? What we only learned 3. One of them doesn't couple. So it's got to be one or the other.
Grignard.
It's a Grignard. And we know that because of magnesium. Right, so this is CM. Obviously, this is C for carbon. And this is M. Right, and then on the other side, The halogen is my X. And that carbon right there is my R. All right, so what I'm trying to do is put together, and the mechanisms vary depending on what the metal is, and there are lots of different ways to do couplings. This is only a fraction of a fraction of the ways that you actually can do coupling. There are so many different methods now that, I mean, you can basically put any two carbon pieces together at this point. All right, so in the product, I want to bond between, I want to bond between these two carbons right here. This one and that one. So what I'm going to do is I'm going to draw this is one carbon right here. I'm just going to indicate that carbon with a dot, the carbon that was bonded to magnesium. And then that's going to be bonded to this carbon, which is attached to that vinyl system. All right, and then the rest of it is, we'll just call it MgI2. Right, this is MX, and this is CR. Questions about that? It's important to understand this part right here. Right, you can't just fuse those two together. So if I were to draw it, and I'm going to erase this, but I just want to show you what I'm talking about. So if I were to just draw this, like that, that's not correct. Right, I don't want to fuse them together. I want to put a bond between the two carbons. So this is incorrect. Right, so I always want to be mindful of where the carbons are that I'm trying to put together. All right, let's do the last example. Help me identify CM and RA. Then we'll come back to the Gilman.
Is that that's the XR?
Yes. And the way we identify the RX is to look for a halogen or some other leaving group. Again, like a triflate or tosylate or something in that family. And then by default, the other side has to be what?
Yes, the CM.
Right, where the metal is here and the carbon is here. So I'm trying to put a bond between this carbon and this carbon. Since you already annotated, do you want to take a stab at drawing the product?
Sure. Series. Okay. So. And that's the carbon. Gonna connect to. That's bad. Anyway, that's the double bond, and then the other CH3.
Oh, okay.
It looks really good because
okay.
I have less screen. I have less space on my screen, so that.
Yeah, it's okay. Let me zoom out. Okay, so it looks like you have a, let me see, you got a, so this is where your two molecules are connected. Right now, this carbon right here, that's over here, let me change colors. that will be this carbon. But you still have a carbon here that's bonded to magnesium. And so what you have to do in this case is to, this is you're in the ballpark, but what you have to do is keep those carbons separate. So this is one. And I'm going to draw a bond to the other one. I know it looks clunky, but it's okay. And then here.
Okay, so I fused them together, but
Mhm.
I should have made another one.
But it's okay. That's a good attempt, especially with this, with us just not touching this. So that's okay. But that's what you want to avoid. So the way I kind of show how to avoid that is to write a dot on each carbon you want to put together. Then that way you'll know to put a bond between those carbons.
Okay, cool.
Mm-hmm. Yeah, thank you for that. All right, let's go back up to the top example. And we have what type of reagent is this one? We're doing this second example right here.
Gilman.
It's a Gilman reagent. We know that because of the copper. Right, so once we identify the organometallic, we know that some part of that organometallic is going to be CM. Right, so this is obviously copper is my metal. This is my carbon. Right, and then I'm going to be reacting that with this, which is RX. I can always identify X by the halogen. All right, so what am I putting together? So with the Gilman, we have to remember a couple of things. Number one, we have to remember that it's still going to couple like a normal organometallic, but only one of these is going to get transferred. So even though you have two of those attached to your copper, only one is going to get transferred over. All right, so let me draw the product and then we'll go back and talk about what happened. So that's a 3-carbon chain that's attached. So I'm going to draw that first. And I'll put a dot on that N carbon that I want to connect. And that's going to connect here. And that's what the product is going to look like. So I have that plus right, that copper, which still has one of those 3-carbon chains on it. And then what was my X? Sorry, iodine. Plus lithium iodide. Right. So the lithium is coming from here. Remember that Gilman is actually, that carbon has not the carbon, the copper has a negative charge. And then it has lithium as a counter ion. So whenever that iodine leaves from the alkyl halide, it's going to end up with lithium. So that's how I end up with this. Right, and then the copper is just by itself with one group still attached. So you only transfer one of those groups. I'll write that in here. All right. Questions about that?
When you say it only transfer one of the groups,
Mhm.
about the two that's referring to the,
Yes, because if we were to draw that out, it would look like this, right? It would have too many carbons. Right, that's what it would look like. Because remember, with the Gilman, when you make it, you use 2 equivalents of your alkyl lithium or organolithium, and you react that with 1 mole of copper iodide. So you actually get 2 of those groups attached to copper covalently. Right, but you can also write it like this with a subscript, and it means the same thing.
okay, awesome.
Good question. All right, and that second example, or the third example, right? I have 2 moles of an alkyl lithium. I got copper iodide, ether, and minus 78 degrees Celsius. What am I doing there? What's that process? That's not a coupling, is it? What reaction is that? Where you take a organolithium species and copper iodide and mix them together. What am I trying to do there? And it's 2 moles of it.
Is that the cuprate that we saw in the notes last time?
Yes, it is. So that's how you make them, right? That's the synthesis of a cuprate. So it's going to end up being copper. What is that? Plus lithium iodide. Let me move this up some. All right. So this is actually how we make the Gilman reagent. All right. Any questions about the coupling, the synthesis, anything?
How do you spell cuprate properly?
It's just cuprate. Right. Other questions? All right. So the next, I guess the next phase of the concept of organometallics is to discuss organometallic addition to carbonyls. Normally, the granular is the preferred choice of adding an organometallic to a carbonyl, and it is a way to synthesize alcohols. All right. So let's move on. We'll come back to this question right here because this is actually a retro synthesis question, working backwards. And we're not ready to do that yet. right? So let's talk about that. So alcohol synthesis through addition of granules to carbonyls. And let me add a page here because I want to give a generic overview first. So let me take this. All right, so when we have a carbonyl, let me jog your memory. All right, so from part one, we talked about functional groups. You can have a aldehyde, ketone, or an ester. Right, if you add a nucleophile like a granule to any one of these, I'm just going to give the basic mechanism. If you add a nucleophile like a granule to any one of these, it's going to attack that carbonyl carbon. Right? Every one of these is going to go through the same type of intermediate. Once that carbonyl carbon is attacked, right, you're going to get this, what's called a tetrahedral intermediate. Every one of these reactions is going to go through this intermediate. And this intermediate, depending on what type of carbonyl you're using, is going to determine the outcome of the reaction, right? So here, normally this reaction, when I add a granule to a carbonyl, I do it in 2 steps. I add the granule first, and then I come back and I quench it with some proton source, right? It can be any acid. It can be, normally it's a weak acid like acetic acid or something like that. Right, but when I add this in, this is how I generate my alcohol. So it's going to be here. Right, that's how I get the alcohol. I add the organometallic, and then I get the intermediate, and then I quench it with a proton source. So I do a proton transfer. Same with a ketone. Right, if I run that same reaction with a nucleophile, in this case, my nucleophile, I'm assuming it to be a granule, right? The same thing is going to happen. This is going to attack here. And I'm going to get this intermediate, tetrahedral intermediate. Same, and then the same thing, I'll have a quench step, right? Where I just add in H plus. That quench is going to do a lot of, it's going to protonate the alcohol, but it's also going to use up the rest of the granule as well, right? Because the granule is very sensitive to protic solvents or acids, and so it's going to basically use up whatever's left of the granule also, right? So then I'll have this as my alcohol. All right, so with a ketone and aldehyde, you can do granule addition and go directly to alcohols, right? If you start with a aldehyde, you're going to get a secondary alcohol. If you start with a ketone, you're going to get a tertiary alcohol. Right, so ketone will give you a tertiary alcohol in the product after adding a granule to it, and aldehyde to give you a secondary. If you start with an ester, this is dependent on the stoichiometry. Right, it's dependent on the stoichiometry. If I react this ester with one equivalent or 1 mole of a nucleophile, I'm going to get to this tetrahedral intermediate. Right, but this doesn't stay here, it actually decomposes. So when it does, that's actually going to give me a ketone. Right, that's again stoichiometry dependent. If I only use 1 mole of my nucleophile. Now if I use 2 moles, let me show you what happens there. What do you think is going to happen? Just give me a hypothesis on what you think will happen with 2 moles.
Let's see. 2
What happens with
moles.
1 mole?
With 1 mole, you form a ketone.
Okay, good. You get a ketone when you use 1 mole. What do you think is going to happen if I add another mole of that nucleophile in? So with 1 mole, let me just let's shorten this because we've already seen what 1 mole will do. Right, we're going to get a ketone. What happens when I add another mole of nucleophile to the ketone? What happened up here when I added a nucleophile to my ketone?
Oh, you
It
formed.
became a-
Oh,
You got an alcohol.
Get alcohol. So with the ester, depending on the stoichiometry, if you use 1 mole, you're going to get a ketone. If you use 2 moles and then quench it, then you'll end up with an alcohol, right? Because now I have this intermediate. Start over. So I got that intermediate, and then I'm here. And then all I need to do now is quench that. So then whatever my nucleophile is, if and this is going to be a tertiary alcohol. Whatever my nucleophile is, if I'm adding that to an ester, the outcome is going to be dependent on whether I'm adding 1 mole of nucleophile or 2 moles. If I add 2, I'm going to get an alcohol. If I add 1 mole, I'm going to get a ketone. Only with the ester. With the ketone and aldehyde, you go directly to your alcohol. All right, questions about that part? All right, so we have 3 different carbonyls that we can utilize: aldehydes, ketones, esters, and we can generate either alcohols or ketones depending on the stoichiometry, right? So with aldehydes and ketones, you react that with your nucleophile, you get alcohol. With an ester, you can generate a ketone or you can generate an alcohol. It just depends on the stoichiometry. All right, questions? Any questions about anything?
The ketone that we make from the ester,
Mhm.
is it gonna be, which? Is it going to be a third, second, or?
Oh, no. So for good question. That's a great question. For carbonyls, there's no bond order as far as primary, secondary, or tertiary. It's because the carbon is sp2 hybridized, right? So it can only have 2 groups attached to it anyway. So all carbonyls are sp2. So they're all going to have the same basic structure, this trigonal structure, right? Where you have a group here, a group here, and a group here. That's a good question, though. All right, other questions? All right, well, let's look at some examples. This top part here is just kind of an overview of the mechanism using the Grignard, showing the Grignard as your nucleophile. The only thing I want to point out here is in the intermediate, right? With the Grignard, remember this is polarized. You got a carbon here, you got your magnesium here. This is partially negative, this is partially positive. So when that Grignard attacks like so, right, and you get to the intermediate, the magnesium that's in the Grignard is going to find that oxygen, right? Because remember what I just showed you in the intermediate, the oxygen has a negative charge. Right, so when I get to that point, the quench step is here, where I just add in some acid. And let me say this: the acid itself is going to have a proton, and then it's also going to have a conjugate base like attached to it. So let's say, for instance, if I used HCl, it can be any acid, but if I use HCl, very dilute HCl, over here, the proton is going here, but the chlorine is going to be here. Right? So that's for any acid. Whatever acid you use, the conjugate base always ends up with magnesium. Let me write that out. So it's going to become a salt with magnesium, always. So any acid that you use, you're going to end up making a salt with whatever the conjugate base. If it's HCl, if it's HBr, if it's acetic acid, it doesn't matter. right? You're always going to end up with that acid, with the conjugate base of that acid being a salt with magnesium. And we can do that down here, right? Let's say for this example, H3O is just a generic acid. I'm gonna make this acetic acid. All right, so here's my granular. And it's this carbon, that's the nucleophile. So it's that carbon that's going to be attacking your carbonyl. All right, so in this example right here, if I follow the mechanism up top, it doesn't change, by the way. No matter what your granule is, no matter what your carbonyl is, the mechanism will never change, right? I'm going to attack here. Like that, and I'll break that carbon oxygen pi bond. So then my intermediate, and I'll advise you to actually write out the intermediate every time. It's going to look like this, right? Where I have a CH3, and then I have a 4 carbon chain. I'm gonna change colors here. Oxygen is negative, and then the magnesium is here, right? It's all magnesium is always going to find that oxygen in the intermediate. Questions about that? So it's the carbon. I get this question a lot, but it's the carbon and everything attached to it in that granule that goes and attacks, right? But the carbon itself that's connected to the metal is the carbon that's going to actually be your nucleophile. I always get that question. As long as I've been teaching this class, I always get the same question about the nucleophile. It's like, to simplify it, is in the most simple terms, it's like a train, right? So whatever's connected to that carbon, wherever that carbon goes, everything else goes with it. So that's why I have this 4 carbon chain there. Now the next step is to add in the acid. So it's the proton right here that's going to end up on the oxygen to make my alcohol. And then it's the rest of it is going to end up with magnesium, the conjugate base, right? So I'm going to steal this because we're almost out of time. So this is going to be here. And then the salt that's left over is going to be acetate anion, and then the magnesium iodide. That when I write out HOAC, hopefully that's not a stumbling block, but acetic acid looks like this. So the OAC part is this piece right here. And then obviously the H is that. That OAC, we call it an acetate. Right, so it doesn't matter what the acid is, the conjugate base of that acid is always going to end up with magnesium. And then the proton from that acid is going to be used to protonate the oxygen, do proton transfer, and get your alcohol. What type of alcohol is that? Is it primary, secondary, or tertiary? And how can I predict that from the beginning without seeing the product?
Tertiary alcohol.
It's tertiary, I agree. How can I predict that from my start material? I should be able to predict it, right? I'm starting with a ketone. If I start with a ketone, then I should get what in the product?
tertiary alcohol.
tertiary alcohol. If I start with an aldehyde, I should get a secondary alcohol. If I start with an ester, then I'm either going to get, depending on the stoichiometry, a ketone or a tertiary alcohol, depending on how much of my nucleophile I add in. All right. So here in this example, we're not going to finish it, but this is one mole, and this is 1 mole. So when they're 1-to-1 like that, it's automatic that you're going to get a ketone as the product. I don't know if I think I did. Didn't I send those granule videos out Friday? Organometallics. I think it was like 2 videos, or maybe it was just 1. It may have
Yes.
been.
Just
Yeah.
one.
It was just the organometallic one. It wasn't the video dealing with carbonyl addition. Am I right?
Yes, you're right.
Okay. All right. I'll send that today. That'll reinforce what we talked about. I'm gonna stop right here though, because we only got a minute left. Any questions from anybody about anything before we stop?